Hey there, everyone. My name is Ryan Schul. Welcome to my YouTube channel. So, in the discussion today, I want to talk about multi-hospital emergency room load forecasting. So, this is how many people potentially can come into an emergency room and need immediate medical attention, and route optimization, right? So, we're going to optimize the route that the ambulance takes to get to the hospital, but it might not necessarily be the closest hospital. So, there's a few different scenarios that can play out. There's a car accident, maybe a possible burn victim or something. The ambulance comes up and they punch into Google Maps. Okay, what's the closest hospital? Okay, they hit the gas and they're off. But what if there's a big delay or a big queue at that hospital and you can maybe get there in 5 or 10 minutes, but the patient is going to have to wait maybe 60 minutes, hypothetically, like whatever the case may be. But if you have to wait a long time, plus the travel time, it probably doesn't make sense if you can drive further away and go to a different hospital, maybe 15 or 20-minute drive for the ambulance, right? But maybe you can get into the emergency room within 5 to 10 minutes, right? So there's a few different ways to optimize this problem. Let's jump into it and try to understand how we can make predictions for the ER wait time and load balance across nearby hospitals, right? So it's a pretty fascinating problem. And this can seriously save people's lives, right? If you get to the hospital maybe just 10 minutes faster, maybe you could save that person's life, right? Maybe if there was a delay of 10 minutes or people made a bad decision. Okay, I'm going to go to a closer hospital, but they're all booked up, and then we have to go to a totally different hospital. That can cost somebody their life. Okay, so this is a very serious case study. Okay, we're going to use random forest to look at the best possible outcome here and see what the average time is to get to the hospital based on a few different factors, and then rerun the model based on the output from the random forest and get the true optimized outcome here, right? So the shortest route to the hospital that can accommodate the person the quickest. Okay, so that's the setup here. So I have the time here, or not the time, the script. I have the script here. Let me hit Control Enter to get this kicked off, and they can take you through it. We have a few different things we're looking at. GeoPandas to try to understand geopositioning systems, lat long coordinates, things like this. We also have street names and like intersections and routes that cars can actually drive on, right? So if you have to get from point A to point B, the shortest distance would be a straight line. But a lot of times roads don't go in straight lines, like they will for a while, but then they curve and they turn. So you have to follow the path of the street. You can't just go in a straight line like an airplane does. You have to follow the course of the road, right? So I just ran the script. So I'm going to go ahead and set up some UDFs over here. So this is composite address. This is going to help me get the number, the street, the city, the state, okay, and the postal code. This is the PC postal code. And we're going to use this kind of as a setup to understand the location of the patient, right, where they're now and which hospital they have to get to. And the next step is going to be setting up the queue or the wait time to get into each of these hospitals, right? So we're kind of juggling a few different things here. So scrolling down just a little bit, we have the name, address, latitude, and longitude coordinates, and then the output based on the geometry of the lat long coordinates, the name, and the latitude. Okay, so this is what we came up with. These are actual hospitals located in the city of Seattle. So I chose Seattle as a city. The input is, where is it here? Oh, yeah, it's down here. So it goes down here. Once we run get hospitals, that's the UDF. If I do Control F, you can see that this little string down here, not string, this little function right here gets called over here. Everything gets dumped in and we get this output. So we have Navos West Seattle campus. And if I go search for this, we should find this pretty easily. These are all actual hospitals located within the city of Seattle. Whoops, I meant Google Maps, not that. Okay, so we're dealing with actual hospitals in cities around the United States, Seattle, Washington. I think what they do is spell out these addresses. In Washington, right? 2600 Holden Street. It's coming up with that. I think there's a little glitch here, either in the script or just the way that Google Maps sees this. Navajo Street, Southwest. Okay. And if I go over here, so 98126, I have 2600 SW Holden Street, Seattle, Washington, 98126. Oh, I see what the problem was. So it couldn't actually find it the first time because Southwest is spelled out, and Google Maps uses the abbreviation SW, right? So it was close. Just couldn't find that one, but I think that's fine. We're pretty close to it. If I put the little man over here, I think we can see from the street view what this thing looks like. Okay, so I guess the hospital is over. Wait, that looks residential. Navos. Let me go back a bit here. I went on the wrong street, maybe. Where's Navos? Southwest Holden. This should be it. Maybe the entrance is over here. Maybe that's how they do it. And now we're in 26th Avenue. So this is weird. Let me look at another one. I think it has to do with that naming convention. Sometimes it's SW, sometimes it's Southwest. Let me look at another one over here. Okay, so there's no SW or Southwest. This should be a little bit more accurate. And we could write that into the script. I'm just seeing this for the first time right now. If it's SW, make everything Southwest. If it's Southwest, make everything SW. Just have a standard convention that we work with. So this looks like it's 101 Marion Street. I think that's what we're looking at here. So I don't know Seattle that well. I was there years ago, just a short trip. More, and this says Bourne Avenue, and we're looking for Marion Street. Oh wait, I think this is Marion over here. Yeah, Marion Street. Okay, so the hospital entrance should be like right over here somewhere, I presume. Okay, so that one I think works. Let's just look at one or two others. This one, the address actually got chopped off. So all of this stuff comes from this right here, OSMnx, which is pretty accurate, but you can see it's not like 100% bulletproof here. Let's look at another one. So this is VA Medical Center, Seattle. Enter, okay. This is the parking lot, VA Medical Center. Okay, so we can see that. So this one's spot on. The other one, something got chopped off here. So we might have to come up with a modification to the function just to make this a little cleaner and a little bit more standardized. I just found the script from some documentation. Is that it? I think that's it. And this looks like a big old hospital, UW Medical Neurology, right? And what one were we looking for? University of Washington Medical Center. So this is a whole medical center, I guess. Okay, I guess that's what they're calling it. So that looks pretty much spot on. So probably this SW could be, or maybe add something to the function to say, hey, if it's SW, make it Southwest, NW, Northwest, something like that. So that could be cleaned up a little bit. This one just fell off. I don't know what happened there. University of Washington Medical Center, Northwest. We can search for that. They might have a special address or something, I'm not sure. 1550 Northwest 115th Street, Salem Hospital. So it should have something there. It didn't come through. That's okay. We still have latitude, longitude coordinates, and we see 47714. If we go back here, we should see that right here. 47714. So that is right on, and I'm getting negative 122,339. 122,337. So it's off just by a fraction of a degree. As you go further and further to the right of the decimal place, you get greater precision. I forgot how that works. Something like after the decimal place is thousands of yards and hundreds in 1 yard or something like that. That's a little bit. Let me go over there for a second. I don't want to go off on a big tangent because this video is going to be long anyways. How okay. So the further you go to the right, I know for a fact it gets smaller and smaller. So this could work over here. And there is a degree of error if you don't go far enough to the right, right? So 4 decimal places approximately 10 to 12 yards, 6 approximately 11 centimeters, 7 is centimeter level, 8 is millimeter level, and 15 is nanometer level. I don't think we need 15. I think if we get 4, 10 to 12 yards, and I think that's what we saw over here, it was off by just a tad. 3076, 122, 3076. If I go back here, what was this thing? Sorry, we'll move on just a second. Sometimes I get curious about these things. I have to figure it out. So I'm looking at, oh yeah, wait, no, I did that one. That's why. Oh, wait. Oh, this is it. So I pop that in here. And I see 476499. Okay, 476499, 476494. So we're off by, let's say, 12 yards. I think that's what it was. And this is negative 1223076. If we look here, negative 1223019. So this is going to be off by a little bit here, right? But anyways, we're pretty close. We're in the general vicinity of this, so I'm comfortable with it. So let's move down. At this point, we need to create a network graph. This is how we're going to understand the coordinates of the road system and where the car, or not the car, the ambulance can drive and where it cannot drive, right? So this is actually how Google Maps works. It works on a network graph-based system. So we have to understand the edges, the nodes. The nodes would be the connections or the endpoints, and the connections. And we're looking at the connections. This is going to be the path to get to the endpoint. Okay, so we need network graph to solve this problem. Time travel matrix. I'm going to create a matrix with 2 levels. H is going to be the hospital, and P is going to be the patient location. So we have to understand, where's the hospital located, where's the patient located, how do we get to the patient to the closest hospital. We're going to create a matrix, right, to see what all the different possible combinations are, and then pick the best one. And then after that, we have to swing back and pick the hospital that has the minimal wait time, right? So the closest hospital, I mentioned this at the beginning of the video, the closest hospital is not necessarily the best option for the patient if there's a long queue to get into the emergency room at the closest hospital, okay? So anyways, we have our H and our P. We're going to create all the possible combinations of that. This takes a couple minutes to run, so let me kick it off as I'm talking. So we're looking for all the possible combinations of H's and P's, so hospital and patient, and then derive the travel time matrix based on that, and get the names of all the hospitals, and then all the routes. Again, because this is a network graph, and this is exactly how Google Maps works, we have to understand the routing component of this model, right? So how are we going to route the patient to the closest hospital? And then the next step will be to match the patient with the closest hospital that has the shortest queue, okay? So that is the goal here. So I'm doing all the calculations right now. I'm getting the first routing, so we're going to have to do 2 routings. I'm going to do 1 routing. I'm going to do the random forest regressor, okay? And then we're going to do a second routing based on the output of the random forest regressor. So this could take a couple minutes. Let me pause it here, take a quick break, wait for this to finish up, and I'll be right back. Okay, so this part is finished off. We see we have about, I think 13 different hospitals here, and we have 12 different patients. So here's patient 0, 1, 2, 3, 4. We might have people's names. We might just have an ID. The basic premise for just having the ID is that patients have a right for a right to confidentiality, right? So you don't necessarily want to say, this person's name and address and give away all kinds of sensitive, descriptive information about the patient. So you might likely have only a patient ID. You could have the patient name as well. So in this case, we're looking at all the different campuses or hospitals locations all around Seattle, right? And we're looking at the relationship of each hospital to every other hospital. And we have the assigned hospital right here based on the location of the patient and the closest assigned hospital, and the estimated minimum cost, again, is going to be to get that person to the hospital in the minimal amount of time. So at this point, we have the routes set up. This is optimized, right? So we have generated the most efficient routes and the shortest wait times. But we have to go ahead and run a technique called random forest to go ahead and help us to get a few different features and then predict what is the optimal outcome here, okay? So with the random forest regression model, and there's a few substitutes for this. You can do XGBoost regression. There's a few others that would be able to solve this problem, but this is kind of a multifaceted problem, so you need something that is going to be able to handle these types of predictions. So certainly random forest regression would do it. XGBoost regression, I'd have to do a little research to see if there's others. Those would be my two go-tos right there. So we need to create a new matrix here, or new data frame here, with some features like hospital hour. This is hour of the day. The day of the week, DAO is day of the week. Arrival time, 15 minutes. Can we get there within 15 minutes, yes or no? The critical ratio, how critical is the patient? What condition are they in? Boarding into the ambulance, dots and doctors at the hospital, who's available, and beds. So you can see this is somewhat of a fairly complex problem. It's not super complex, but it's not too hard to solve. We'll get to the solution in just a bit, but I would also like to say at this point that you'd need some kind of real data system, probably Kafka. That would be my go-to for this type of thing. We would have to have this system updating in real time constantly throughout the day. So how many doctors are assigned to that hospital based on the hour of the day of the week, the doctor schedules. Does somebody have to be on call and they have to come in because they're home, they're not at the hospital? So there's a few different variables that need to be handled in real time. And again, it's not too hard to get this set up, but to make this model really work really effectively, you can't just run the scenario and and expect everything to just run perfectly. You have to have like a little bit more architecture here. So my background is data science, machine learning, AI, DL, things like this, finance. I got my MBA in finance, but I'm not a network architect, right? So you really have to have like a real-time system that's constantly processing all this information, which doctors are on call, which doctors are actually in the hospital, how many beds are there in the hospital, right? So this is a quick drop-in solution for a problem that's somewhat complex, but not too complex. But to make this really sexy and really work in real time, you would need like a real architecture behind this. This is just a Jupyter notebook running on my laptop, okay? This is not an architecture solution here. But you can see where we're going. So these are the independent variables. This is the dependent. The dependent is dependent on these. These are all independent. And the wait minutes really depends on these variables over here. I'm not going to get into all the details because I have several videos on my channel about machine learning, what's an independent variable, what's a dependent. So Google it. I've got tons of videos on my channel. Use ChatGPT, whatever method you need to help you to understand these concepts. If I'm talking about something here and it doesn't resonate strongly with you, use Google. Google is actually a skill. Google is a skill. So we're setting this as a dependent variable, and all of these are independent. So the dependent is dependent on the independent, right? So we set up the model, train it, test it, fit it, and we have the final outcome here. The wait time is based on a random forest predictor. RS is the model that I set up over here. You can see RF is the random forest. We fit it right here with the X training and the Y training, and the X comes from here, right? And the Y comes from here. So again, I'm not going to go into the whole history of machine learning, but I guarantee this is set up correctly, okay? So hopefully you understand. I'm going to assume that most of this makes sense. If not, again, Google it or use ChatGPT. So the random forest regressor says there's a mean average error of about 3.87 minutes. So it could deviate about 3.87 minutes depending on a few different factors that we have no control over. Traffic conditions at that time of day, the day of the week. Is it a weekday? Is it a weekend? Maybe weather conditions, maybe even some weird thing like, I don't know, the ambulance gets a flat tire or something. I don't know. There's variables that we can't control for, right? But on average, the model should be pretty accurate with a deviation of about 3.87 minutes. 3.87 seconds. Okay, sorry. Hopefully, we're not that far off. About close to 4 minutes, the model could be off in its predictions. So that is a little bit, but 4 minutes is not a whole lot of time. Although, in a mission critical situation, if this is life and death, and the person needs to get there, maybe 4 minutes could make a difference. But again, we've got this model in a pretty good state. So there's a few things we could do to maybe improve. We could add a few hyperparameters, pick the HGBoost regressor. Like I said before, we could test different things. I'm not trying to make this absolutely precision perfect. I'm trying to set the background for an interesting case study here, and I'm trying to show you how to solve it. Okay, so here again we have the routing next. So we have the routing first at the beginning, right? So here's the routing first. We use XGBoost regressor to get the best solution. Now we have our routing next, okay? Now we can rerun the original algorithm because we have the updates from the random forest model, right? So that's the intermediate step, running the first sequence to get all the times for the ambulance to get to the hospital and what is the shortest queue at the closest hospital, right? And we have to juggle that around a little bit to get the optimal solution, right? Then we run random forest. The objective then becomes travel time plus predicted weights, okay? So we know what the weights have been in the past, but we have to make a prediction into the future about what the next weight is going to be because we don't know. We know historically what has been in the past, and we can use that history to make predictions into the future. That's the whole point of doing this, right? So routing with just travel time or just some initial weight now really kind of we're going to come up short in our predictions, right? The second table is after the weights have changed, right? After we random forest regressor and tweak the inputs. Now we have travel plus wait time prediction, okay? So in a nutshell, we're rerunning the routing and what lets the system respond to a cognitive rather than just distance, right? A live congestion rather than just distance. So that's why we're doing that. So you can see it's a multifaceted problem. What's the closest hospital? What is, and that's going to give us the distance, right? Based on where the ambulance is now. But also we want to know what the congestion possibilities are right now, because at midnight on a Monday is going to be very different from a Saturday afternoon. And that's going to be very different from a Friday 5 to 6 p.m. rush hour, okay? So let's move to the next step. Okay, so now we have the percent changed, the average cost basis, the average cost new basis. So we have the original and the new, and then the delta average. So this tells us the average cost basis is 5.25 minutes. The average new updates is 8.83 minutes. So the average cost actually adds 3.57 minutes, right? But we really have to swing back again and really make sure that we're comparing apples with apples and getting the best routing opportunity here for the ambulance to get to the hospital, the closest hospital that can accommodate this patient, okay? So I'm rerunning the whole process now, looking at all the possible combinations of hospitals that we can go to, the real-time traffic conditions, and the queues at each hospital, okay? So now the percentage of people that have been rerouted is actually 83%. So in the first scenario, we're just going to the first closest hospital, but that really isn't the best hospital in 83.3% of the cases. So in about 17% of the cases or so, the closest hospital is the best option, but 83% of the time we have to reroute the patients to a different hospital, okay? So the average cost base is 5.25 minutes. The total cost new is 8.31 minutes, and the increase is 3.06 minutes. But it looks like things are actually getting worse. We actually added 3 minutes to the total time, including the commute time and the queue time at the hospital. So is this solution really working for us? We're adding 3 minutes to the time that it takes the patient to get to the hospital, right? But we have to keep in mind the base case is based only on travel time. The new case is based on travel and wait time, okay? Remember, we use the random forest as an intermediate step. We use the first step to get all the waits and travel times to the hospital. Random forest gave us the updated outcome based on current traffic conditions, right? That's why this is a multifaceted problem, and we really need to use a solution like Kafka and really have an architecture built on that. And I would argue that even in some cases, if you have enough deep history, like probably Monday morning, Tuesday afternoon, Wednesday evening, Thursday overnight, Friday morning, and Friday evening, over a long period of time, are probably going to have pretty consistent and persistent traffic patterns. So if you couldn't get access to real-time data, if you get deep historical data, I think the analysis would still be pretty accurate and be pretty relevant. Okay, so when we add new runs, this adds wait minutes into the cost function. So what we really need to test for is whether the average stay with wait, going to the local hospital and waiting a little bit longer, is that better than reroute with a wait? Okay, so should we stay on course where we are and wait in a short queue or maybe a long queue, or reroute and wait in a short or long queue, right? So that's the next step we have to solve for that next. So we have the patient ID stay cost minimum, the reroute cost minimum, the improvements in terms of minutes, the base hospital and the new hospital, to see is there going to be a change in the hospital where this person is recommended to go to. So again, we get the best routing 83.3% of the time. We should make a change between the initial hospital and some updated hospital, because only 70% of the time, the closest hospital is actually the best bet. So the base hospital here is Swedish Medical Center, Ballard campus. The recommended would be C-Wing. This one has been updated. This, I'm not sure what that is. Maybe a data quality issue. This has been rerouted. This has been rerouted. This, and this. So all these have been rerouted, right? And about 83.3% of the time, we will see changes in the recommendation where the ambulance needs to go. And you can see over here the improvement gain in terms of minutes. Here we've shaved off 12 minutes. Here's 11.4, 9 minutes saved. Down here, 4 minutes. That's 4 minutes, right? This is 45 seconds, 45 seconds. There's still an improvement, not huge, but almost a minute. This is 12 seconds saved. Okay, so in all these cases, if we reroute the ambulance to a different hospital, it's going to benefit the patient. But even if we can get actual street-by-street routes from the original library I introduced you to back at the beginning, the OSMnx graph, print turn-by-turn instructions for both the baseline and rerouted optimized routes. We can also absolutely do that using this model down here. So again, this is based on graphing technology, right? This is exactly how Google Maps works. I have one video on my channel that breaks this down and shows you all the details of graphs, nodes, and edges. So we're going back to the graph library because this is really the best way to solve this type of problem. And we are looking for these types of features in our data frame. So the name norm, that's the original hospital, the bearing, the length, and the total travel time. Okay, and we have to understand the instructions, the street, the distance, and the estimated time in minutes to get there. So I'm not sure if I ran this. Let me run it now. Control Enter to run. So we have the instruction, street, distance, estimated time, and we have the final output here. So the total distance from the patient to the nearest hospital is 3.76 kilometers, estimated time to get there, 5.7 minutes. This is the original hospital right here. We have the turn-by-turn street directions right here. This is Navos West Seattle campus. Then, based on the analysis we did before, this is being updated to VA Medical Center. The total distance is 8.89 kilometers, and the estimated time is 10.3 minutes. And let me just take a quick step back. I'm just looking at one patient ID. This is PID, patient number 4. So I'm just going to focus on one single patient just for the driving instructions. But I'll show you at the end how we can optimize this for all of the patients. I'm just not going to print out all the driving directions for all the patients. I'm just showing you here how you can dive a little bit deeper and get the turn-by-turn directions, right? So these are all the directions here, and here's the directions. So this is the original recommended hospital, 3.76 kilometers, 5.7 minutes to get there. The updated recommendation, 8.89 kilometers, 10.3 minutes to get there. So when you look at it, these numbers are actually increasing. We go from 5.7 minutes, almost doubling, 10.3, 3.76 kilometers, almost tripling it to 8.89. So is this whole scenario actually working, or are we just making things worse, right? We're doing a lot of lift here, big lift, but it seems like things are getting worse. But that's not really true, right? So the table says a constant cost minimum is 15.24. Now I'm going to redo this because I ran the analysis before and it generates this data for me dynamically because I don't have access to this hospital data, right? I don't have the real-time historical downtown Seattle data. I don't have this, so I had to generate it to test this concept and to make it work. If I have this data, or if you have this data, you can plug it in and it's going to work right out of the box. I don't have the data, so I have to manufacture it, or what's it called? Not curate, just create the data myself. I have to create synthetic data, right? So we have 3.76 kilometers. So let me update this because I did the analysis before. It changed a little bit. And the total reroute cost is 10.518. So 8.89 is the reroute, right? Wait, let me just see. Stay cost minutes. Oh, I'm sorry, minutes. 5.7 and 10.3. Okay, so here's minutes. Wait, let me go back there. I think this was right. 15.204 Navos cost reroute minimum is 10.58. Okay, so we actually have to go back a step. 15.204. So this is patient ID. We should find patient ID right here. Patient number 4, 15.20. And the reroute cost is 10.51. Improved minutes is 4.86. So you take the delta between that, 15.2 minus 10.5, you get 4.6. The original recommended hospital was this. The updated hospital is this. Okay, again, we're just looking at one patient just to get the turn-by-turn directions. And in the end, I'll show you how to do this for all patients simultaneously. So we shaved off 4.68 minutes, almost 5 minutes. We're rerouting from this original hospital to this new updated hospital. Okay, so that is fine there. Turn-by-turn directions 5.7 versus 10.3, so we just saw that. So here's the 5.7, 10.3. Okay, so the travel penalty is 0.46 minutes. So it looks like it's getting worse, right? And we're doing a disservice to this patient, but we really have to understand the weight savings time, right? Because there's less of a queue in the second hospital, even though it takes longer to get there, we really are saving a lot more time. So the weight savings includes the improvement plus the travel penalty. So the improvement is 4.68. The travel penalty is 4.6. So we really save 9.29 minutes. So why should we do all this work, right? I think it's apparent at this point. You can't just say, okay, the ambulance is at this point in Seattle, whatever cross streets, northwest, east, south, whatever it is, and the closest hospital is, this far away. And Google Maps will take you to the closest hospital, but if there's a 60-minute queue to get into the emergency room, it doesn't make sense, right? Look for the closest hospital that has the shortest queue. That's what we're trying to accomplish here. So we're looking at travel time, queue time, and the decision includes the total, which is the drive and the wait for each patient. So in this scenario down here, I can go ahead and do the update for all the patients simultaneously. Remember, we just looked at patient 4 before, right? PID is number 4. You can do this for any patient. Look at the estimated original travel time to that hospital. That's more travel time, but the queue at this hospital is much shorter than the queue at this hospital. So the total savings in terms of minutes is 9.29 minutes. So hopefully that makes sense. That was only for patient number 4. If we do this for all the patients, we can see everything in its entirety, right? And we can see all of the baseline minutes, the new minutes, travel penalty, and the weight savings in terms of minutes. Here's 12 minutes saved, 13 minutes almost 60 seconds, 9.3 minutes, 0 and 0. So just go to the closest hospital. This is a hospital change in the first 8 instances. Yes, we're going to make an update, reroute the ambulance to a different hospital based on current traffic conditions, distance to the hospital, and the queue time. So we have 8 updates. 2, there's no change in the rerouting to a new hospital. We just say with the original recommendation or the closest hospital, whatever Google Maps is telling us, and we go there, and that is the best possible outcome to save the patient, right? So hopefully this makes sense. I made a few assumptions. It's pretty accurate. It's pretty realistic. I don't have this hooked up to Kafka. I would love to have that. I would love to see that. I don't have deep time series analysis of traffic in Chicago. Again, I'd love to have that. I would love to see that data. I don't have that. But if we had that data, we could just plug everything in and hit the play button and get these outputs in real time, right? Because Kafka is a real-time system, constantly updating every couple of seconds. Maybe if there's not a high throughput and not tons and tons of data being analyzed, maybe in a fraction of a second, we could get the results, right? And we could have the screen update constantly. So the medical or the medics, I don't even know what they're called on the ambulance, but the medics on the ambulance can get these real-time updates and make real-time decisions and make informed, intelligent decisions to try to save as many people's lives as I can when time is a major factor, right? So that's it, guys. I'm going to save this. I will give you all the source code. I think this one was pretty interesting. It took me a little while to do the research and get everything straightened out and fine-tuned and optimized and all that stuff. But I did learn quite a few things doing this exercise, so it's totally worth it for me. I'd invite you to take a look, and hopefully it's worth it for you too. So that's it, guys. I am going to wrap it up here. We are at 36 minutes, pushing 37. That's it. I covered everything I want to cover. This is finished as far as I'm concerned, okay? Thanks for your time today, and I'll see you in the next one. Goodbye for now.